Hello everyone. As we all know, at times the shortest path is not always the safe path, and sometimes you do not know which path would turn out to be risky. So, in such a condition, how does a robot operate? Don't worry, the RAGS algorithm is here to help us understand of how to avoid this. So let's dive right in. So let's first understand the problem that RAGS algorithm is solving, right? So in a real world scenario, the environment is unstructured. Hence, we need an algorithm that is not only fast, but also has the ability to operate under uncertainty. Since it is an unstructured environment, the true cost of the edges are dynamically revealed when the robot approaches these edges. So how do we tackle this problem? RAGS will help us achieve this, and let's look into more detail. So the RAGS algorithm is used to handle this assumption that the map is highly certain and the edge costs are static. But in the real world scenario, that's not the case. The maps have a high uncertainty and there can be a dynamic reveal of costs. So RAG's algorithm has the ability to handle this. Also, most algorithms that try to solve this issue usually have a huge blow up in the computation time, but RAGS takes care of this by deciding when to be conservative and when to be aggressive. So it has a live feedback for the decision maker. It also can determine the edge cost using a probability distribution. Here we use a normal distribution. There can be other forms of distribution that we can look into. So now let's understand the mathematics on how to solve this problem. Let's understand the problem formulation. First, we consider the graph G, which contains all the vertices and their edge cost, which are derived from the normal distribution. We make an important assumption here that when queried, the edge costs are drawn as independent and identically distributed samples from the cost distributions. So in the image below, we see a start or the current robot's point and the neighboring point vertex A, B, C, D, and so on. Here we just consider A, B to understand the concept. As we can see, A contains M acyclic paths to the goal and B contains N acyclic paths to the goal. So the first question that naturally rises is, what is an acyclic path? Acyclic path is nothing but a path that does not loop back to the start. So it is a continuous path. So coming back to our first question, that how do we find the cost from the start to the goal via the point or vertex A? So it is given by this formula here. This formula represents nothing but saying that the cost to the vertex A is the sum of the edge cost from the current position to vertex A and the lowest cost path from A to the goal. So using the same analogy, we can determine the decision criteria for other vertex, and the below formula here, it basically indicates that if you move to vertex V, then the probability the path cost is lower than any other vertex V is greater than 50%. So now let's understand on how to quantify the path risk and the effects of the mean and variance. The probability that the lowest cost path in A is lower than B can be written as follows. So this is just an update from the previous slide. Here we have two terms in the integral. The second term is given by f of x comma a and the first term is given by g of x comma b. Here f of x comma a is the probability that the best path along the vertex A has a cost less than x. And this is where we want to understand what would be effects on the graph of f of x comma a versus the threshold. So let's look into the next slide about the details regarding the graph. So here the black line is where the mean is 20 and the variance is 5, and this is our starting point. From here we'll compare what happens to the graph based on this line. So first let's look on what happens if we increase the path set size. So on increasing the path set size, as we see, the dark blue and the light blue lines represent that we added one element and then we added two elements, and we see that the graph shifts to the left, so the transition to reach one is more rapid. But another thing that we notice here is that it does get rapid, but the gap between them keeps decreasing. So eventually over time we'll get diminishing returns, so it won't be that much helpful. But yes, at the start we can see there's a huge change and then a slow change, and then this will keep dropping down. Now let's look at, after we have seen the path set size, let's look at the mean, effect of mean. So here by adding paths with lower means and higher means. So the first one, the one with the orange color, is where we reduce the mean and we observe that the transition is much faster to reach one. And in case of the higher mean, the yellow line, it's just overlapping with this, so there is no effect to it. Another property that which we can check is the variance. So on lowering the variance, that is represented by the purple line, we see that the transition to 1 is faster, but for the first part of the cycle it's slower than the path sets which we increase, but eventually as we increase the x slightly more, it reaches transition to 1 much faster than the other two lines. Now what happens if we do a higher variance? That is represented by this green line. So as we see, it flattens out kind of, and this is not good because this has high uncertainty in its prediction, and this won't help much. So now let's look at what can we conclude from this analysis. What did we get from this? The whole purpose of the analysis before was to show that how we could decide the most relevant path for our calculations. As we saw, higher means and variances are the ones that are the worst. So we could naively just penalize and discard these paths. However, because we consider the cost defined by normal distribution with equal variation around mean, a path with large cost variance has equal chance of resulting in both more and less costly traversals. Moreover, these probabilities are higher than those of paths with lower cost variance, but the same mean cost. As a result, punishing pathways with high variance too harshly might lead to a loss of optimality. So we could now either do an update to the partial ordering criterion to trade off the mean and variances based on the probabilistic path risk as shown in the previous slides. Now, before moving on to the pseudocode, let's look into the topic of non-dominated path set and the threshold. So the RAGS algorithm performs two sweeps, wherein the initial sweep is to determine the cost to go for each node in order to consider the path risk during its execution. And the domination threshold helps contain the number of dominated paths. So the natural question arises, what happens in the above equation if d equals 1? So when d equals 1, the number of dominated paths tends to 0. Also, if the d is equal to 0.5, then the non-dominated path set reduces to the paths with optimal mean cost. Also, in the range of 0.5 to 1, there's a guarantee that a star algorithm path would lie in it. So now let's look into the pseudocode to have a better understanding on how this code works. So now let's look into the pseudocode. As we can see, the RAGS algorithm performs an initial sweep from line 1 to 17 to look for the non-dominated path set, and the second sweep is performed during the execution to integrate the edge cost information as it is received. Lines 1 to 17 display the initial sweep, which has some variations when compared to a star. Let's look into them. So if the current node has a path from start to goal, it is included in the non-dominated path set, and this can be seen in the lines 8 and 9. Also on line 14, each child node of the current and large node is verified against the ancestor list in order to clearly rule out looping pathways. A child node is also eliminated at this point if it is discovered to be dominated by any closed set node with the same end vertex. The first sweep is halted. The third difference which we can observe is that the first sweep is halted in line 16 when the open set is empty or when any node in the current non-dominated path set is determined to be dominated by the next node to be enlarged from the open set. The directed graph created by this non-dominated path set is the first step in the RAGS online execution, and this can be observed in line 18 of the code. Each edge transition starting at the start vertex on line 20 evaluates the set of all nearby vertices as shown in line 23 and computes a total ordering of potential traversals as seen in line 24. If the information is available, RAGS incorporates the observed cost of the upcoming transitions here. And finally on line 25 we observe that the best vertex from the set is executed and this loop runs until the goal vertex is reached. Now let's see what this algorithm brings and compared to other algorithms. Before moving on to the comparison, let's look at the Diax output. So on the graph A, we can see the edge variances are marked in different colors. And the one with the darker blue represents a lower variance. And on graph B is the red color indicates the non-dominated path set, and the black indicates the path selected by the RAGS algorithm. So now let's do a comparison with different types of algorithms. So here we have performed a comparison of RAGs with the greedy algorithm, the naive A-star algorithm, the sampled A-star algorithm. And the results from 100 unique graph configurations are plotted below, and they are done using the Monte Carlo test as it's a random sample from the probability distribution. So graph 1 shows the path cost to variation to the different values of threshold. Graph 2 shows the planning time versus the different values of thresholds. Graph 3 shows the path set size versus the different values of threshold. So let's look into the graph 1. We can observe that the performance of the greedy algorithm deteriorates over time. So the purple one is the greedy algorithm, and we see that it's deteriorating over time as we increase the threshold. But the performance of sampled A-star increases over time. And this is essentially due to the fact that the computation time for RAGs will increase as well. So it's permitting the sampled A-star to apply a bigger quantity of Monte Carlo graph samples to decide the very last accomplished path. Also, we can see that RAGS is outperforming A-star for a range of 0.5 to 0.65, but starts performing poorly post that. This shows that more paths added to the non-dominated path set do not produce better results. Hence, RAGS is most beneficial when used for lower values of threshold. RAGS is also capable to consider a large set of feasible paths in comparison with sampled A-star for the two most important reasons. As you can see here, the number of paths set size is much higher, and this is because first, the sampled A-star desires to attract values from all aspect value distributions and run the A-star look for every Monte Carlo query. In comparison, RAGS most effectively runs a single search via the graph throughout the preliminary sweep and leverages the coarse domination metric to address the node growth ordering. Also second, the RAGS online execution is enormously speedy in comparison with the preliminary sweep. This is due to the natural path set pruning that happens throughout the execution, in which after every aspect traversal, the closing path segments results to the goal shrinking, thereby making the calculation much faster. So now let's look into the results on the satellite data. Now we are observing RAGs being applied to some satellite data, and these are some experiments that are conducted by the authors of the paper. So first, the satellite images are filtered to find potential obstacles such as tree. How do we find these obstacles? So simply we can use a Gaussian filter to locally homogenize the image, and then the trees can be extracted using the pixel color, and the output is shown here. And now let's look at what is the graph that we can make out of this. So I'll be proceeding to the next slide. Now we can construct a graph by randomly sampling the space, right? So here we can see that this is how the graph is created. Also, to assess the cost of flight ways, we calculate the mean and variance of the recognized pixel over each edge and utilize these values to characterize the edge cost. So now let's look at some results in comparison with the A-star algorithm. So the test on performing on the satellite data, we see the following results. And we do not plot for sampled A-star or greedy search so as to avoid clutter. So first figure, it's a pretty straightforward start to end point. There's no trees in between or obstacles, and all the algorithms successfully reach the point in the same manner. Figure 2, we can see that we're basically demonstrating that all these algorithms can actually track around the obstacles. Figure 3 is where things start getting interesting. And we see that RAGS does take a longer path, but it's a much safer path, and it's not from the obstacle dense environment. Also, even though it's taking a longer path, the time to reach is shorter. Hence, Also, the time to reach and the cost both are shorter compared to the A-star algorithm. And figure 4, we see that A-star clearly outperforms RAGS because RAGS algorithm is trying to be as safe as it can, and it leads to a slightly higher cost. Not a much difference, but still A-star has a lower cost in this case. So that's all on the satellite data. Let's get a real action. Let's put this on a drone and see if RAG's algorithm is actually implementable into the real world. So now we'll be looking into the flight trial data in the next slide. The goal of this test was to reach the finished location in the fastest way possible. So here we are using a DGI matrix M100 for these tests. We can observe that RAGS took a longer path, but took less time when compared to the A-star. And these hardware trials show that RAGS algorithm can be applied onto the real world, and second, it will attempt to reduce the risk by choosing a safer path. And here we can clearly see that the path length for RAGS is higher, but the travel time is lower because it does not have to dynamically change its path always to avoid these, as it's already going through a not a very dense obstacle environment. So now let's look into the conclusion that we can derive out of this. From the experiments and flight trials, one can easily conclude that the RAGS algorithm is a combination of the traditional deterministic search approach combined with the risk-aware planning. And this is helping us minimize the risk associated with executing a costly path. So despite having longer paths in order to maintain the distance from obstacles, the RAGS algorithm does reach more quickly. And the authors did talk about the future work for this algorithm. And the first one being the cost can be represented using different distributions, not just the normal distribution. We could opt for the log normal or the beta distribution, which could lead to more accurate results. Second, the RAGS can be applied for information optimization, for which the edge cost distribution would demonstrate an environmental information. So overall, the RAGS framework has great potential and good application in the field of probabilistic planning. So thank you, and I thank the authors of the paper to give such great knowledge regarding this. Thank you.